My name is Simon Steele. I'm the Senior Director of Education STEM Programs at the SETI Institute. And I'm speaking today with Michael Busch, a planetary astronomer at the SETI Institute. And we're going to talk about a discovery that was made last August. And it was a discovery of a comet. So we asked, what's special about a comet? There's lots of comets known. What's special about this comet, Michael, that we're talking about?
So we talked a bit about this last September, shortly after this comet was found. It's called 2I Borisov. Borisov is the name of the discoverer, Gennady Vladimirovich Borisov, who is an astronomer, amateur astronomer, engineer is his day job. He builds his own telescopes, he looks at various things, working out of the Ukraine. He has found several comets. End of August of last year, he found a comet that followed a very strange orbit. It comes into our solar system from the outside. This is not from around here. Did you want me to switch over to the screen sharing and I can show them the orbit?
Yes, because I mean, I suppose the question is where do normal comets come from, and how do we know that this has come from somewhere else? Let's have a look at some of the graphics here.
All right, so the screen sharing is working correctly. You can see this, Simon? Hopefully That means they can also see it, the audience.
Yes.
We have on the right here the trajectory of 2I Borisov relative to the orbits of the planets in the inner solar system. We are, of course, down here on Earth. This is as of last October. We've moved around in our orbit, so we are back over here now. Mm-hmm. Borisov came in from interstellar space, looped around the sun, a bit further out than Mars, and then looped back out into interstellar space. It's on its way out again now, and it's not coming back.
Okay.
So this comet got ejected from its own solar system, presumably around some other star, 1 billion years ago or more. It spent a very long time in interstellar space in the middle of nowhere, and then just happened to pass near the sun. Mm-hmm. We hadn't seen anything like this until pretty recently. We'd seen asteroids get kicked out of the solar system. They fly by Jupiter, doing what we do with spacecraft. We're sending them to the outer solar system, just naturally happening by chance. And they speed up so much that they go off into the void and they'll come back. So only recently, astronomical surveys focusing on discovering asteroids and comets have found a couple of things coming into our solar system from the outside.
Mm-hmm. So this is, we'll come back to the
And I must emphasize here that Gennady Borisov found this thing. He's running his own telescope. It's not a specialist survey program that found this thing. Yeah. He just happened to look near the sun on the sky. This comet came in from an orbit that made it hard to see from the ground or from Earth orbit for a long time. Borisov has been very careful to look where most survey programs are not looking, and thus he finds things they don't.
So this is a long tradition, isn't it, of amateurs finding comets? So this goes all the way back to Charles Messier and before, where you've got people looking for comets, seeking out comets, and so this is a different one because this has actually come in from another solar system. And you said that our solar system is also sort of ejecting comets into interstellar space as well. Yes. So we're reciprocating in a way to other planetary systems.
There was a question we had asking the astronomical community for a very long time now. We see how often things get kicked out by Jupiter. So is that typical? Mm-hmm. Well, now we know the last 20 years or so that there are lots of Jupiter-sized planets on orbits around the stars. So this ejection process can be happening. We have multiple star systems where you can loop around one star and then kick by the other one and you fly away that way. But how often was that happening? We did not know. Now we have 2 examples of interstellar objects that have been found coming in, other than microscopic dust. Borisov is 2I, 2 interstellar in the catalog. There is 1 interstellar, which is an object now called Oumuamua, which is an asteroid, not a comet, so far as we can tell. It looks like a rock. Maybe it had a little bit of gas that came off, ice that evaporated into space when it came near the sun. That is now also outbound. It's much further away than Borisov is now because it came by a year or so earlier and thus kept on going. It is now much further away.
So is it, I mean, when Oumuamua came through this, we didn't know the frequency of stuff coming through our solar system. This could be a once in 1,000 years, once in a million years thing. Now we've had two coming through in quick succession. Does that say, is that just a freak, or does this tell us something that this is actually not as rare an event as we thought it was?
So with two interstellar objects, we can start doing statistics, but our uncertainties are really, really big. The Vera Rubin Observatory, which is now being built in Chile, has done a lot of analysis of all the different things they expect to find with their survey programs. They had a prediction they would find roughly one interstellar object per year of probably a few hundred meters across. Oumuamua was about 100 meters wide. The nucleus at the center of Borisov is about 500 meters, so a third of a mile across. These are not very large objects by the standards of asteroids, but there's more small things than large things. So it's this balancing act of rare large interstellar objects might be easier to see, but they don't come by very often, versus the really small things you just can't see at all. So there is this sort of one per year expectation with current and upcoming telescopes that we'll be able to find more things like this.
Right.
But we still don't know that well, because with two objects, it could be 50% higher or 50% lower, and it wouldn't be unsurprising. It wouldn't be surprising, sorry.
Yeah. Now, looking at your slide here, you've got the orbital part. It's actually not an orbit, is it? You've got the path of the comet.
It is a very nice hyperbola.
Yes.
Now, one caution here: this is projected down onto the plane of the Earth's orbit. It's actually coming in at a very steep angle. It does not care the direction that the planets go around the sun. It's just coming in from some random direction in interstellar space.
Right. So if we imagine the solar system, most of the planets are aligned in the same plane.
Plus or minus a few degrees. This is coming in from, I have to look it up, several tens of degrees off from that.
Coming down onto the disk of our solar system. This is...
It's falling through at a pretty steep angle, and then falling out on the other side.
Okay.
Falling is wrong. It's actually flying up. But gravity is weird. Official astronomer opinion, gravity is weird. Okay.
Well, it is. You've got a picture, an image on the left-hand side of your slide, and that's the Hubble Space Telescope image. So as you're saying, this is tiny. So what you're
seeing in that picture there is not the nucleus, the central part of the ice ball that's in the middle of the comet. That is mostly ejected gas and dust. It's come off of the surface. Okay. So we see comets coming in from the outer Oort cloud in the solar system. We infer they form in a similar environment to Borisov in terms of the types of ice that we see coming off. I say we, I have not done these observations. Many astronomers have. They get all the credit. I'm just looking at this. So Hubble Space Telescope images here show you some tails of gas and dust coming off. That's mostly being driven by the solar wind pushing things around after it gets ejected off the nucleus. So the tail is roughly outwards from the sun, which, given where Borisov is now, the tail is actually in front of it. This was the image on the left was before closest approach, so the tail was behind it as it came in. Okay. So the numbers down at the bottom there, just when it got to closest approach to the Earth and to the sun. Closest approach to the sun, it gets about twice as far away from the sun as we are. We are at 1 AU, 1 astronomical unit from the sun. That's the average distance between the Earth and the sun. It goes up and down a bit depending on the time of year. Borisov was about twice as far away from both the sun as the Earth is, and from the Earth as the Earth is from the sun. So this was never anywhere near us in terms of the scale of the solar system. In terms of the scale of interstellar space, of course, this is very, very, very close. Oumuamua, the other one that I mentioned, came in quite a bit closer to the Earth, was actually not seen until after close approach. This is a bit frustrating because even if you are observing near the sun on the sky, you can't look right next to the sun when you're observing from the ground. And so you miss things when they're coming from that direction, which is a big section of the sky. There was a bit of a period of time between October and early this year when even the Hubble Space Telescope could not look at Borisov because we were on the wrong side of the sun. So you see the orbit here, Earth is down here, Borisov is coming through, it's on top in the image, it's basically on the opposite side of the sun from us for a few months. So there was that interruption. Since Earth has moved around enough that the comet can be observed again by telescopes on the ground and Earth orbit, there have been a bunch more observations, and those are the new results we were talking about today.
Okay. So this image, the Hubble Space Telescope image, when we look at this, you say that the nucleus, even with the Hubble, is a pinpoint. It's too small to see. How big is this corona, this mass of gas coming?
We actually have a scale on the next slide, which shows the new pictures.
Yeah, okay.
So the image on the right here is one of the most recent images of Borisov, with thanks to Qicheng Zheng down at Caltech, who is a graduate student there, who has, as part of his thesis research, been doing a repeated series of images of Borisov. So this is the current image of the comet. It's, apologies, I'm going to go back to remind myself. It's now about 3 times further away from us than we are from the sun, and a bit more than that from the sun itself. So a bit further away, it stopped being quite as active, with an exception. But you see the scale here. That scale bar at the bottom is about 2,000 kilometers.
Right.
So that's, do the division by 1.6 there, 1,300 some miles. And the coma is, depending on how you draw it, here, several hundred to several thousand kilometers across.
And that just
it doesn't have a sharp boundary. It's relatively dense near the nucleus, and then it drops off as things get further and further away.
And that's what you're seeing in the images on the left, which are the what are called false color images, aren't they? And
so all of the stuff here is false color. The one before is closer to what you'd actually see with your eyes. But here it's just, these are different ways of representing the brightness on the image. It's all monochrome. It would just be gray if I took the raw data itself.
Right.
The relevant thing for this series of images here is we're seeing now images of Borisov over March and into early April. Initially, it was just a dot, single pinpoint nucleus. But you'll notice the images on March 28th and March 30th in the middle of the screen here. It is no longer a dot. It is elongated this way. What's actually going on in there is that there's 2 dots. Borisov broke apart. So we see this happen with comets fairly frequently, actually. If they get too close into the sun, they heat up too much and they can completely vaporize. Or they can get spun up by stuff evaporating off one side more than the other, and then they break apart, literally exploding. Or they can actually have progressive erosion and just keep eroding, and then the comet breaks into pieces that way. So 67P, the comet visited by the Cheremiah Gerasimenko, the comet visited by the Rosetta spacecraft, that will probably eventually just fragment because it looks kind of like a duck right now, and the neck is going to erode. That's probably not what happened here. This is more likely a process of thermal expansion. You have the object getting heated up because it's interstellar space. It's minus 270 Celsius, very, very cold for 1 billion years. It comes into our inner solar system, 2 AU from the sun. It warms up to only a minus 100 C.
That's a big
more
difference.
or less. And that's enough to vaporize some degree of the water ice, but also ice of carbon dioxide, carbon monoxide, methane. And if you have material on the inside below the surface, it takes a few months to heat up. The heat from the sun works its way inward. So even though it's well past its closest point to the sun, apparently something decided to abruptly expand, and presumably that was some ice turning into vapor. There's some other possible explanations. People are still trying to understand what happened here. But based off the relative brightness of the different pieces here, it looks like out of the 500-meter wide nucleus of Borisov, something about 100 meters across broke off and flew away into space a couple of weeks ago.
So
now the next interesting point is that piece then proceeded to disintegrate even further, because if we look at it, the image on the right, that's from last week, it is just a dot again. So the big central part of the comet is still there, and that'll presumably survive all the way back into interstellar space. But the piece that came off just kept on breaking, and now it's just invisible dust.
So it really has just disintegrated. It's not like 2 lumps. It's that
not anymore.
Disintegrated. Yeah.
And in this progressive fragmentation, again, we see with comets in our own solar system. I had been planning some years ago now to do observations of a comet. I was part of a team planning to do observations of a comet called Swassmann-Bachmann 3. Except when we went to look at it, there were 6 pieces of comet. Then there were 60.
Mm-hmm.
Then there were so many that it became impossible to track them all anymore.
Mm-hmm.
So one of the interesting parts about Borisov here is, as unusual as it is, it didn't come from around here, been in interstellar space for 1 billion years. It actually looks and acts an awful lot like comets we're familiar with.
How does it compare, say, chemically? I mean, we know
in terms of the
roughly.
ices, it looks a lot like the mixture of materials we see for comets in our solar system. There's water ice, there's some dust, which is rocky material, little carbon compounds mixed in, presumably a little bit of metal, but that's impossible to tell from here. And then there's also other types of ice, carbon dioxide, carbon monoxide, methane, nitrogen.
Yeah.
So it looks like something we'd see in our outer solar system in the Kuiper Belt.
Okay.
Just it came in from the outside.
Mm-hmm.
One thing I have been wondering about is if people can get results on the isotopes of different elements present in the gas coming off the comet.
Mm-hmm.
I have not seen the results of that yet. It would be pretty hard to do.
Yeah.
But you'd expect those to be different. We see this in our own solar system.
Mm-hmm.
Depending on where you are, the initial mix of material, you get pretty wide ranges in the different isotopes that are present.
Right.
The overall chemical composition may be the same, but over here you'll have 1 part in 1,000 of deuterium, or whatever number of thousand of deuterium. Over here you'll have half as much. So you expect it to look different in that regard from anything we've seen, but I don't know if anybody succeeded in getting those measurements yet.
Okay. I'm trying to anticipate what some of the questions will be about this comet, and one of them, scientists, astronomers are very good at predicting where things are from and where things are going, because they all follow the laws of physics, the laws of gravitation. Is there any concept of where this came from? Can you be
So
that?
it gets a little bit tricky because we know we think we understand how gravity works pretty well, but Borisov is not moving around strictly under gravity. It's doing this nice hyperbola by the sun, but even when it was found, it was already putting out all of this gas and dust in the tail.
Mm-hmm.
And depending on how exactly that comes off the nucleus, that's pushing it around significantly. This makes running the orbit backwards in time pretty difficult. Initially, the uncertainty was dominated by how well we measure where it was.
Mm-hmm.
Now we've got data from September through April, so that's 6-7 months of data on the orbit. It's pretty well determined, and the uncertainty becomes how much was it jetting around before it was discovered, and we just don't know.
Mm-hmm.
But with those uncertainties, you could run the orbit backwards out into interstellar space. You take into account the gravity field of the galaxies as well as we know it, and you can then take all the star motions that have been measured by things like the Gaia spacecraft from the European Space Agency, and you can try to figure out where all the stars were relative to where Oumuamua was, and Borisov for both of these cases.
Mm-hmm.
Oumuamua is easier because it wasn't jetting around as much. But in both cases, you can run them back a few million, 10 million years, and then the uncertainties in the position become a large fraction of a light year. And you can't say it was actually near the star or not.
Mm-hmm.
And nobody has found them near anything.
Okay.
But this probably is not surprising. If you have an object that's ejected out into interstellar space from some star somewhere, probably remains in space for billions of years before it passes near anything else.
Mm-hmm.
Just based off of allowing that's a few astronomical units away from a star to be counted as a close pass, and allowing that stars are tens of thousands of astronomical units apart.
Mm-hmm.
So it's not surprising that we can't tell where this one came from, because in just random draw, there was maybe 1 chance in 100 that you could do that. If it's average of 1 billion years flying around, not near anything, and then only 10 million years you can track things back.
Mm-hmm.
If we should at some point have the fortune to have seen 100 interstellar objects come through, maybe figure out where one came from.
Mm-hmm. And there might be a pattern there, and
at that point, we'd understand a whole lot more about what's actually out there in interstellar space,
mm-hmm.
which would be interesting by itself. So
So
find more of these things is, of course, a goal of the survey programs.
So Oumuamua and Borisov, they didn't come from the same place. These are very, very different objects. Coming
Different
from
objects, they're on different
places.
trajectories, they're traveling at very different speeds.
Mm-hmm.
And they were offset from each other by, in interstellar space, the distance the sun moves in interstellar space in roughly a year.
Mm.
So what is the sun's orbital velocity around the galactic center in astronomical units? they're offset from each other by tens of astronomical units.
Mm-hmm. Mm-hmm.
So they're not related to each other.
Yeah. Okay.
Neither in position nor velocity nor composition do they match.
Mm-hmm.
And this is an interesting point. There's apparently a fairly wide range of stuff that's getting thrown into interstellar space.
And we've got two very different things. If they were two comets, then that might suggest that that's what they're all out there. But
the first two we find are really different from one another.
Yeah.
So again, motivation to find more.
No, I know Oumuamua, and we missed a close approach. Only got it when it was heading out.
Yes.
There were suspicions, and the first grown-up sci-fi book I ever read was Rendezvous with Rama, 1973, I think, Arthur C. Clarke, about an alien spacecraft moving through our solar system. And, there was some interest in Oumuamua in terms of it looked rather peculiar, at least from its radar signature.
We did not get radar observations of Oumuamua. Oh. We could not do that because we only knew about it well after it would have been close enough to get a radar observation up. In terms of infrared and visible light and spectral people obtained there, Oumuamua looks like a rock. Mm-hmm. It acts like a rock. It tumbles around as if it were a solid pile of rocks.
Yeah.
Borisov acts like a comet and it looks like one too. So
comet.
These are not alien spacecraft. I will say that with extremely high confidence.
Okay. The question had to be asked,
and it probably will be asked by some of the viewers. So, also, I wish we had better references than Arthur C. Clarke on alien spacecraft coming in. Mm-hmm. So there's just so many problems with Rendezvous with Rama.
So you mentioned Rosetta and its rendezvous with a comet back in 2014.
Yes.
It would be nice, wouldn't it, to sort of catch up with one of these interstellar visitors. Technically, how would that work? Can you foresee that happening more in the future?
So I got asked this question the previous two times we talked about interstellar objects coming through. And people have studied this. There's a couple of aerospace engineers who amused themselves by running out trajectories. So these things are coming in from very far outside the orbital plane of the solar system. Mm-hmm. And they're traveling so fast that they are going to go up into interstellar space and not come back. So at a minimum, you need to go as fast as they are going, and you need to go in the direction they are going. In order to change the orbital plane of your spacecraft that much, you start, of course, in the Earth's orbital plane. The simplest thing to do is to fly by Jupiter. And you aim yourself underneath Jupiter, or on top of Jupiter's north and south poles. You've turned off the screen sharing, that's okay. So I could gesture at the trajectory of Oumuamua, but the whole point now is that it's not in the plane of the planets. Mm-hmm. Mm-hmm. So if you go by Jupiter and underneath or above, depending on your frame of reference, and you just throw your orbit on the appropriate angle to line up with where the object is going. Then you loop back down near the sun, get as close as you can, and use your much rocket fuel as you can to accelerate up in that direction. Mm-hmm. You go close to the sun here because it's more efficient in terms of going to escape speed or above that if you make the velocity change near the sun versus far away. Mm-hmm. Even in that case, you may not be going fast enough, and you might have to invoke something like nuclear electric propulsion, which people have talked about for spacecraft missions, Pluto orbiters, that kind of thing, just to catch up with the object. Mm-hmm. But even then, models people run, biggest rockets we have available, lifting the largest amount of material, it would take you something like 30 years just to catch up. Mm-hmm. And now you're out in deep interstellar space, and you stop you're flying by this thing at some pretty high speed. If you want to stop when you get there, that's even harder. Mm-hmm. So most likely, all that will be able to happen with these things is flybys of them very briefly when they're close to the sun. Mm-hmm. This is now being done with a project called Comet Interceptor that is getting built by the European Space Agency. It had been in proposal phase when Oumuamua was discovered, and now, of course, Borisov is available. So the mission's proposal is that they will park a spacecraft in Earth orbit, and they will design it so that it can sit there for several years at a time, mm-hmm. without any problems. And then, given that somebody comes in that they discover they can fly the spacecraft by, they will fly the spacecraft out there. The relative velocity is going to be really, really, really high because they're not targeting their orbit based off of that whole procedure I described for matching the velocity. They're just going to arrange that they get not quite run over by the comet as it comes into the inner solar system.
Mm-hmm.
It's not certain that they'll find a thing the thing will be found that they can fly by during the mission.
Mm-hmm.
In that case, they'll go fly by some more prosaic or cloud comet as it comes in,
Mm-hmm.
which is already exciting enough because we haven't flown by such a thing with any spacecraft. But that's pretty much all you could do is just arrange one very brief flyby and not much else.
Right, sort of like a New Horizons type. You've got to make sure your cameras are on as you shoot past.
So it's even more extreme than that because New Horizons is not going anywhere near as fast as these things are at the sun.
Mm-hmm. Wow. Yeah. What about? I mean, these are, as you say, are very, very small objects. They're relatively speaking, 500 meters or something. You said,
right? For Borisov.
And when that's out in the outer solar system, of course, it's not outgassing at all. It's just a device. How easy is it to find things this size or bigger? How close are they going to be? You know,
so Oumuamua was found. It's not outgassing when it was about 1/6 as far away from the Earth as the Earth is from the sun. Mm-hmm. So that was very, very close, astronomically speaking. Borisov was found again about well over twice as far away, but that was because it was putting out so much dust and gas that it had this big tail thousands of kilometers wide, and that a lot easier to find.
Yeah. Mm-hmm. So to catch these early, they'd have to be quite big objects.
And there aren't that many of those.
There are not that many. Fortunately, perhaps, that they're not big things.
Although with only a sample size of 2, we don't have that many constraints on how many big ones and how many small ones there are. We can do the size distribution of things that get ejected from our solar system. Mm-hmm. And you can say for every 1,000 things like Borisov, there should be one thing that's 10 kilometers wide or whatever the number ends up being. It's that kind of a ratio. But we don't really know what that should be for interstellar objects because it's a sample size of 2, big uncertainties.
Yeah. Could there be planets out there wandering through space?
Probably. If you look at models of planet formation, a significant quantity of planets do get ejected, but that's sort of 1 per star level. Mm-hmm. And stars are really far apart. So rogue planets are not something that we expect to come near us anytime soon.
Okay.
People do look for things like Jupiter that are big enough that stay a bit warm from their gravitational accretion that heats them up. Those you can find a light year away with infrared telescopes. Mm-hmm. There aren't any within a light year, people have looked.
Mm-hmm. That's good. I remember another science fiction movie called When Worlds Collide, which was an interesting...
but that is not something that is going to happen. I'll say that with high confidence.
Well, I think that's possibly a good, maybe not a good place to end, but a nice way to wrap this up. Thank you very much, Michael, for talking about Comet Borisov. If you want more information on this, do check because we'll be putting up links to relevant papers and articles. And if you are interested, sorry you couldn't, for technical reasons, join into this conversation, but please do put your comments online when this video is posted, and we'll try and respond to you. And but otherwise, thank you, Michael, again, and we will see everybody with Spacebook Live next week.